Hello again. This is Roger Koch Barr for the Bioelectricity course, and we have reached week number 4. And in this week, we unravel the mystery of where action potentials come from. So, here we are. And I have used as the analogy for this week, building train cars. Now, the reason I chose this analogy is that a train can have lots of different kinds of cars: passenger cars, dining cars, mail cars, freight cars, all sorts of cars. Action potentials are the same way. They may seem to be one event, like the whole train, but they have a series of things that happen one after another in a synchronized and linked way. And that's how it all comes about. Within this week, we will talk in some detail about the Hodgkin-Huxley membrane model. The Hodgkin-Huxley membrane model is the original membrane model that showed in a carefully integrated way how the different parts of the action potential come together. Hodgkin and Huxley put their model together from experimental data. So in that sense, it is an experimental model. However, they went further, and they represented their findings and explained the model in mathematical terms. So the Hodgkin-Huxley membrane model is very strongly based experimentally, but it also is a mathematical and a conceptual model, and we want to see it from all its different dimensions. An important part of the Hodgkin-Huxley model is that it provides the basis for numerical calculations. So we'll talk about those some too. Generally speaking, within this week, in the first group of topics, these topics, we'll talk about the need to explain the action potential. That is to say, to explain the mechanism by which the action potential comes about. And then in the latter half of the week, this part, we'll talk primarily about the numerical model that one can use. So let's review what is the problem exactly. It's easy lots of times in bioelectricity to get lost in individual topics and forget what the problem is that one is trying to solve. Well, here we have a rather clear-cut problem. If we look at passive tissue and we apply a stimulus to it, in this case we're applying a stimulus from outside the tissue, but it would be equally true for a naturally occurring stimulus. In passive tissue, there's a little bump in response to the tissue, and then nothing more. Now the problem is, but also the wonderful feature is, that in active tissue, after that little bump, there is a huge response thereafter, which is called an action potential. However, the model that we had, this model, did not explain where that action potential came from, and in fact it seemed to even rule it out, because at the end of the stimulus, we had a charge capacitor. So we had charges here and here, minuses there and there. We understood passive tissue because we understood how the charges could flow through the resistor and come back over here, and as a result how the capacitance could discharge over time. But there's just no way here that one can possibly explain a large secondary or large subsequent deflection, which we call the action potential. So our problem is we've got to explain that. So Hodgkin and Huxley in the mid-1900s provided such an explanation. Let's talk about what they did a little bit just historically. First of all, they recorded data from the nerve axon of the giant squid. So a giant squid is probably the creature for whom the ancient sea monsters were modeled after. If you think of a basketball court, the size of a basketball court, then a squid is enormous, even in relation to the size of a basketball court. So it's, a giant squid is something like what people call an octopus in cartoons. It's a giant octopus. And within that squid, there is a large nerve that goes from the head down here to the bottom of the body. It's a nerve that has a very large diameter. Giant squids are rarely seen, but occasionally they are brought up from the ocean. And Hodgkin and Huxley studied the nerve of the giant squid when giant squids were brought into shore at the Woods Hole Institute in the northeastern United States. They studied the giant squid because the axon itself was giant. If we look at a sketch, we'd say the thing that made the giant squid nerve different from other nerves was the fact that its diameter, the diameter of the nerve was large enough that it was possible to place within that nerve some wires. You could actually push wires down the center. So they would push at least 2 wires. So here there's a wire that I have as a red wire and another wire that I have as a green wire. There are wonderful descriptions of this in the literature, if you have time to look them up, that show pictures and show exactly step by step, really well worth reading. So if you think about now what they do with the wires, they put corresponding wires outside, and they can use them, the pairs of wires, to measure the voltage from the inside to the outside. They can use other pairs of wires Here I've used the green wires. They can use the second pair of wires to pass currents through the membrane. And by doing combinations of voltages and currents, they can deduce how the membrane is working. At least that was their goal. It wasn't easy, so they had to do it carefully and repetitively. Additionally, the fact that the wires went from one end to the other was, for the purpose of understanding, an advantage, because it meant that the same thing was happening all up and down the whole entire fiber. So this entire fiber is, as people call it now, space clamped. I'll write that, space clamped. Which means there can be no variation as you move from place to place. It's all clamped together as far as sites. So any changes that they saw, since it was space clamped, had to be changes that were occurring somehow or other across the membrane. The fact that they had the squid axon in an experimental apparatus gave them a number of advantages, but two advantages that were important to the experiments were, first, they could change the composition of the solution. I'll just draw it as if it's coming out on a fire hose here. They could change the composition of the solution outside the axon, and by changing the composition of the solution, they could introduce solutions that had more sodium ions or fewer sodium ions or more potassium or less potassium, or whatever compositional changes they wanted to have. As you know, when you change the concentration of the ions, you change the Nernst potential across the membrane. Then the second thing they could do, correlated with the first, did that. They knew the compositions of the solutions, so they could set the voltages to the equilibrium potentials, the Nernst potentials, of different ions and watch what happened, which then had to be coming from other ions. So if they set the potential to the Nernst potential for sodium, they knew that sodium ions wouldn't move, and the movements that were observed, whatever they were, had to be from potassium, and vice versa. So that gave them some degree of flexibility in figuring out what was going on. The core idea of the Hodgkin-Huxley model was to do the following thing, to say, look, the problem with the passive model is this current, it's the resistive current, because this axon is not just a resistor. Rather, what we will do is replace that resistive current with a set of three currents, one for sodium, one for potassium, and one for everything else put together, chloride ions plus all other ions. So they have one for sodium, one for potassium, one for all others, which they call leakage, and determine what happens on each of these pathways separately. And by doing that, they created a model that could explain action potentials. We will come back and study this model in more detail. The important thing they did, from our point of view, is not only did they describe their experimental findings, but they described them mathematically. That is to say, in equations, so we can pick up the equations and use them in other contexts. For the mathematical theory and for the work as a whole, Hodgkin and Huxley received the Nobel Prize. At that point, they were already very famous. And the work itself, not the prize, but the work itself, was so meritorious in the sense of introducing so many ideas that explained what was seen in experiments. It was so meritorious that it became the basis of quite a lot of work in understanding the squid axon and understanding other axons, and then by creating new models as extensions of the Hodgkin-Huxley model in understanding other kinds of excitable tissue. Thank you for watching this segment, and we'll come back and talk in somewhat more detail about the Hodgkin-Huxley model and the ideas underneath it.